On a mountaintop in northern Chile, a camera the size of a small car has just begun something no instrument in the history of astronomy has ever attempted. Not a single photograph, not even a handful of images, a continuous 10-year-long movie of the entire visible universe, capturing every visible change, every explosion, every flicker of light across the southern sky every few nights for an entire decade. And in just the first few hours of testing the system, scientists were already looking at results that left them stunned. This is the story of the Vera C. Rubin Observatory, and why its latest images are being called one of the most significant developments in the history of observational astronomy. If discoveries like this fascinate you, hit subscribe now, because we break down the biggest developments in space exploration every single week. Let's start with what makes this observatory fundamentally different from anything that's come before it. Perched at the summit of Cerro Pachón in Chile, chosen specifically for its dry air and exceptionally dark skies, the Vera C. Rubin Observatory represents the culmination of more than 2 decades of planning, engineering, and construction. It's a joint project funded by the U.S. National Science Foundation and the Department of Energy, built around an 8.4-meter telescope paired with the largest digital camera ever constructed, feeding into a data processing system built specifically to handle a genuinely unprecedented flood of astronomical information. That combination, an enormous telescope and the largest camera ever built, exists for one specific, ambitious purpose. Rather than capturing occasional, carefully planned images of individual objects, the way most telescopes throughout history have operated, Rubin Observatory is designed to continuously scan the entire visible southern sky, repeatedly every few nights for 10 consecutive years, in a program called the Legacy Survey of Space and Time. Here's why that approach represents such a fundamental shift in how astronomy actually gets done. Like this video right now, if you want to understand exactly why scanning the same sky repeatedly, rather than searching for new objects one at a time, could reveal things no previous telescope was ever capable of finding. Most telescopes throughout astronomical history have operated like a camera, taking individual, carefully composed photographs, pointing at one specific target, gathering detailed data, then moving on to the next target. Rubin Observatory operates more like a continuous ultra-high-definition security camera pointed at the entire sky, recording everything that changes, night after night, for years on end. That distinction matters enormously because a huge amount of what happens in the universe isn't static. Stars explode, asteroids move, distant galaxies flicker as supermassive black holes at their centers consume surrounding material. Distant supernovae briefly flare into visibility before fading away entirely. A telescope designed to capture single, isolated snapshots will inevitably miss the vast majority of these fleeting, ever-changing cosmic events. A telescope designed to continuously monitor the same regions of sky repeatedly over years catches them. Rubin Observatory officially unveiled its first images to the public on June 23, 2025, during an event in Washington, D.C., and the results immediately demonstrated exactly what this new approach could accomplish. In just over 10 hours of initial test observations, the observatory had already captured millions of galaxies and Milky Way stars, along with thousands of newly detected asteroids. Don't forget to subscribe before we get into exactly what those first images actually showed, because the scale involved is genuinely difficult to comprehend. Among the very first images released, one in particular captured public and scientific attention immediately. Nicknamed the Cosmic Treasure Chest by the observatory's own team, this image revealed a southern region of the Virgo cluster, located roughly 55 million light-years from Earth, alive with detail. Blue and red stars from our own Milky Way galaxy shine prominently in the foreground, while nearby blue spiral galaxies and more distant clusters of red galaxies fill the background. Altogether, the specks of light captured within this single image represent approximately 10 million individual galaxies. Take a moment to actually process that number. 10 million galaxies, captured within a single image during Rubin Observatory's very first public release. And astonishingly, according to the observatory's own team, that staggering number represents just roughly 0.05% of the approximately 20 billion galaxies Rubin Observatory expects to capture over the full course of its planned 10-year survey. A second striking image released during that same debut combined 678 separate individual images, captured over just 7 hours of observing time, to reveal extraordinarily faint details within the Trifid and Lagoon Nebulae, vast clouds of gas, and dust located several thousand light-years from Earth, where new stars are actively being born. By layering hundreds of individual exposures together, Rubin's imaging system revealed structure and detail within these nebulae that would have remained completely invisible using standard single-exposure imaging techniques. Officials attending the debut event described the achievement in strikingly ambitious terms. Michael Kratsios, director of the White House, Office of Science and Technology Policy, stated that Rubin Observatory demonstrates the United States remains at the forefront of international basic science, describing the project as an investment in the future that lays down a cornerstone of knowledge for generations to come. Brian Stone, performing the duties of NSF director at the time, went even further, stating plainly that Rubin Observatory will capture more information about our universe than every optical telescope throughout all of history combined. Here's where the story moves from an impressive debut into something genuinely transformative for how astronomy operates day to day. Make sure you're subscribed, because what happened next fundamentally changed how quickly scientists around the world can respond to new cosmic events. Following its initial debut, Rubin Observatory spent the remainder of 2025 completing final commissioning work and an operational readiness review, preparing to transition from initial testing into full sustained scientific operations. In late February of 2026, the observatory reached a genuinely historic milestone, launching its real-time alert system. On its very first night of operation, February 24th, 2026, Rubin Observatory issued 800,000 individual alerts to astronomers around the world, flagging newly detected asteroids, supernovae explosions, actively feeding supermassive black holes known as active galactic nuclei, and variable stars whose brightness changes measurably over time. That number, 800,000 alerts generated in a single night, represents just an early preview of the observatory's full intended capacity. According to NSF officials, Rubin Observatory is ultimately expected to produce up to 7 million alerts every single night once fully operational, an almost incomprehensible volume of real-time astronomical data flowing continuously to research institutions and astronomers around the globe. Luca Rizzi, a program director for research infrastructure at the National Science Foundation, described the significance of this alert system clearly, explaining that by connecting scientists to a vast, continuous, makes it possible to follow the universe's events as they actually unfold in real time, capturing everything from the most explosive, dramatic cosmic events down to the faintest, most fleeting changes that would have been completely undetectable using previous generations of astronomical survey technology. This alert system has already produced tangible scientific results, well beyond simply demonstrating impressive raw numbers. Among the objects identified through Rubin's early observations, astronomers using the observatory's Simone Survey telescope discovered a new main belt asteroid, cataloged as 2025 MN45, on May 2nd, 2025, even before the observatory's official public debut. That single discovery represents just one small example among what will eventually become an enormous, continuously growing catalog of newly identified asteroids, comets, and other solar system objects, cataloged automatically as Rubin's cameras sweep repeatedly across the sky. There's a particularly important dimension to this ongoing asteroid detection capability worth understanding clearly. Because Rubin Observatory doesn't just capture single images, but instead repeatedly photographs the same regions of sky over and over throughout its 10-year mission, its data processing systems can automatically detect objects that have moved between successive observations, precisely the telltale signature of an asteroid or comet passing through our solar system. That capability makes Rubin Observatory an extraordinarily powerful tool for planetary defense purposes as well, dramatically expanding the total catalog of known near-Earth objects and providing significantly more data points for tracking and refining the orbits of potentially hazardous asteroids over time. Beyond June of 2026 marked another genuinely significant milestone for the observatory. According to researchers at SLAC National Accelerator Laboratory, which jointly operates the facility alongside NSF Noir Lab, Rubin Observatory officially began what scientists describe as capturing the greatest cosmic movie ever made, its full, sustained legacy survey of space and time operations, relentlessly observing the entire southern sky every few nights, to construct an ultra-wide, ultra-high definition, continuous time-lapse record of the universe, stretching across the observatory's full-planned 10-year mission. Researchers involved with the project describe the scientific potential of this ongoing survey in genuinely sweeping terms. According to project scientists, Rubin Observatory is expected to illuminate an enormous treasure trove of discoveries throughout its decade-long mission, including pulsating stars, supernova explosions, the fossil record left behind by ancient galaxy mergers, and crucial new clues regarding the deep, still unresolved mysteries of dark energy and dark matter, and, perhaps most exciting of all, entirely new categories of cosmic phenomena that astronomers haven't even identified or named yet, simply because no previous telescope has ever monitored the sky with this level of continuous, comprehensive coverage. That last point deserves special attention because it represents perhaps the most genuinely exciting aspect of Rubin Observatory's entire mission. Throughout the history of astronomy, many of the universe's most significant phenomena were first identified purely by accident, unexpected signals or brief, fleeting events captured by telescopes that happened to be pointed in the right direction at exactly the right moment. Rubin Observatory, by continuously monitoring the entire visible southern sky rather than focusing narrowly on predetermined targets, dramatically increases the odds of capturing genuinely unprecedented cosmic events. Phenomena so rare, so brief, or so previously undetectable that no existing scientific category or classification currently exists to describe them. It's also worth understanding just how significant the underlying camera technology is to accomplishing all of this. Rubin Observatory's camera, built primarily at the LSST National Accelerator Laboratory, stands as the largest digital camera ever constructed for astronomical purposes, featuring a resolution so extraordinarily high that a single image captured by this system would require hundreds of ultra-high-definition television screens to display at its full native resolution. That level of imaging power, combined with the observatory's wide field of view, allows Rubin to capture enormous swaths of sky in remarkable detail during every single observation, rather than requiring astronomers to choose narrowly between capturing either fine detail or broad coverage, as earlier generations of telescopes typically had to. The sheer scale of data this system generates also required an entirely new approach to data processing and distribution. Rubin Observatory's infrastructure processes incoming images, essentially in real time, automatically comparing each new observation against previous images of the exact same region of sky, specifically searching for anything that has changed, whether that's an object that has moved, a star that has brightened or dimmed, or an entirely new point of light that wasn't present in any previous observation. This automated comparison process is precisely what allows the observatory to generate its enormous nightly stream of alerts, flagging genuinely significant changes for astronomers around the world to investigate further, often within minutes of the original observation actually being captured. Scientists studying dark energy and dark matter, two of the most significant unresolved mysteries in modern physics, have specifically highlighted Rubin Observatory's unique potential to advance these particular fields. Cosmologists, including Josh Freeman and Risa Wexler, reflecting on decades of previous work through projects like the Dark Energy Survey, have described Rubin Observatory as representing a genuine next step forward for this specific area of research, building directly on lessons learned through earlier, smaller-scale survey projects, while dramatically expanding both the total volume and precision of data available for studying how dark energy and dark matter shape the large-scale structure of our universe. Looking ahead, across the remainder of Rubin Observatory's planned 10-year mission, scientists anticipate that the sheer cumulative volume of data collected will fundamentally reshape multiple areas of astronomy simultaneously. From cataloging the vast majority of large near-Earth asteroids for planetary defense purposes, to mapping the distribution of a dark matter across enormous swaths of the observable universe, to potentially discovering entirely new categories of transient cosmic phenomena never previously observed or classified. Rubin Observatory's ongoing legacy survey of space and time represents one of the most ambitious, sustained scientific undertakings in the history of astronomy. For now, having only recently transitioned from initial testing into full, sustained operations, Rubin Observatory has already fundamentally demonstrated exactly the kind of continuous, real-time astronomical monitoring that scientists spent over 2 decades planning and building toward. Millions of galaxies captured within its very first test images. Hundreds of thousands of real-time alerts generated within its very first night of full alert operations, and an entire decade of continuous, unprecedented sky monitoring now officially underway, promising to reveal a version of the universe that no previous generation of astronomers has ever had the tools to actually observe. If this story gave you a new appreciation for just how much we're about to learn about our universe over the next 10 years, make sure you're subscribed, because there are more groundbreaking discoveries like this coming every week. Hit like, drop a comment, letting me know what kind of cosmic discovery you're most excited to see Rubin Observatory make next, and I'll see you in the next video.